Please.
Thank you, Emmanuel. Yeah, it will be a little bit about molecules in the end, but mostly about magnetic atoms. So this is unfortunately not yet your dinner speech, but I'll try to make it entertaining nonetheless. So this is about supersolids, as Emmanuel was saying. And so the question first is, what is actually a supersolid? And that basically can be boiled down to a very old question, whether a solid can also be a superfluid at the same time. And you see, there have been quite a lot of people working on this, thinking about this question. And that is because it is really a counterintuitive thing. Yeah? You're supposed to have a state of matter that has both the rigid crystalline structure of a solid and at the same time the frictionless flow of a superfluid. And the plus sign here in the center, I really mean this as a kind of a quotation mark quantum superposition of these two states of matter. So a prime candidate historically was always solid helium. Well, as you all know, as you cool down helium, it becomes a superfluid. And then if you increase the pressure, actually it can also turn into a solid. And then the idea always was, you have these helium atoms on the crystal lattice, and there are holes in this lattice that can delocalize and then Bose-condense if you're cold enough, and give you a finite superfluid fraction of this solid material. Now, how about that in helium now? So this transition to this supersolid state, that should show up as a change in the moment of inertia of such a system. Obviously, if some of it turns superfluid, there will be a change in this moment of inertia. And people have done a lot of experiments, and it was very famous, very popular in the beginning of the 2000s to look at torsional oscillator experiments. So this is such a torsional oscillator. It rotates. You can basically measure the eigenfrequency of this, and somewhere inside here, there's solid helium. And then, in this experiment, people observed that below a certain temperature, something like 175 millikelvin, there was an abrupt drop in this moment of inertia, change in the eigenfrequency. And so everyone got really excited. After 60 years, they thought, okay, now, or 40 maybe at that point, that state of matter is there. But then it turned out, unfortunately, helium is a very strange material. And at low temperatures, the elastic properties of helium change unexpectedly. And that actually explains all this data. So to date, there's no clear evidence whether supersolidity really exists in helium. Okay, so I told you there's this question, and we are now trying to approach this question the other way around. We're now asking, can a superfluid or a fluid be a solid at the same time? And that's something we can do because we work with cold gases. But I can show you what is actually going on in a very nice analogy. What you see here is a drop of a classical ferrofluid. So it's kind of an oily solution with magnetic nanoparticles inside. And we're going to expose this now to a magnetic field. And you see something very interesting happens here. As we're magnetizing this system, a translational symmetry is broken. And basically what I will tell you about in the following is basically how do we do this in quantum mechanics. And in particular, if we get quantum mechanics involved in this, can we really get this coherent superposition of a fluid and a crystal? So for this, we need to produce a quantum ferrofluid, and the way we do this is we use dysprosium atoms. So dysprosium has a very interesting, very complex electronic structure, which gives you large angular momenta, which in the end gives you a large magnetic moment. In fact, it's the largest one you can find in the periodic table of 10 Bohr magneton. Which means, in contrast to your everyday rubidium Bose-Einstein condensate, for example, we do not only have the normal contact interactions that you may have seen before, but our atoms also interact anisotropically over long distances, just like little magnets. So they're not just billiard balls that are colliding at short range, but they also interact like little tiny classical magnets. Of course, you need to pick your atom in the right way. You always have to compare dipolar interactions and contact interactions, and you want to make the dipolar interactions dominant here. So you need to pick something with a big dipole moment, which is why we are using dysprosium, where, for example, whereas with rubidium you wouldn't see any effects. But basically, putting this all together, we have now a system at hand that has significant dipolar interactions. Because it's atoms, it's actually very simple to cool, and it's also collisionally stable. So, for that reason, it's actually fairly straightforward to produce a Bose-Einstein condensate of these atoms. And now with these Bose-Einstein condensates, you can do experiments. The first one you can do is a classic BEC experiment. You can take a laser beam and steer it through your BEC. And then you measure the Landau critical velocity of this system. Yeah? And it shows you, perhaps not too surprisingly, because it's a BEC, that this is also a superfluid. It's a bit of a weird superfluid because now you have these dipoles that can point in different directions, and whether you polarize them along the direction where your laser is steering or perpendicular to it, you will get different critical velocities. So it's sort of an anisotropic superfluid, but a superfluid nonetheless. And then at the same time, you can basically repeat this experiment that I was showing you a minute ago with the classical ferrofluid, and you can see that this Bose-Einstein condensate can also crystallize into these little droplets and form a kind of a classical crystalline structure. The physics behind that is very deep and very complex. It involves beyond mean field effects that were surprising, were a big surprise when they were first observed. But I'm not going to go into too much detail about that for now. Just believe me, or believe the pictures, that this BEC can form a crystal. And so now the question we need to address is, actually there's another state of matter involved here. Yeah, this is all a gas also, whether this gas can form a solid and a superfluid at the same time. So can this gas form a supersolid? So to make a long story short, you can basically tune in these gases the behavior by tuning the contact interactions, and you can really go transition from a Bose-Einstein condensate to such a classical crystal. This is still a theory calculation here, and we like to do these experiments in like elongated geometries where we get this 1D line of crystal sides. This will become obvious in a second why this is favorable. And then it turns out there's a very small parameter range in between where you actually get something that has sort of still this background, superfluid background of a BEC, and on top of it there is a modulation that forms a crystal. In an experiment, we can just take pictures of this. You see this agrees fairly well. You can also map out phase diagrams, and it basically agrees with all the theory that we know. You can also take this potential supersolid at this point still and let it expand, typical matter wave interference experiment, and you see you form very nice interference patterns. One thing I would like to point out here is that this is not your textbook two-slit experiment anymore, but you're actually interfering multiple of these droplets, and so you're actually getting more peaks here. And every set of peaks allows you to individually resolve first the nearest and next nearest neighbor coherence. Now, again, this can be mapped out, and it's all in agreement with theory, so it's very strong evidence for supersolidity, but it's actually not yet a proof that this is still really superfluid. Yeah? So far, it's just coherent, so to say. Because if we want to learn something really about the superfluidity, we need to look at the elementary excitations of this system. And so for this, it's actually instructive to go away from this finite site system that we realize in the experiment and first look at an infinite system. So what we're doing when we're forming this supersolid is we're breaking two symmetries here. First is the U1 phase invariance. That's the normal thing the BEC already breaks as well. And then we're breaking translational invariance. So if you believe in the Goldstone theorem, then this means that there should be two modes, two gapless Goldstone modes in this system. The first one is just the sound waves of a BEC, and the second one is the phonon of the crystal. So this is a self-assembled crystal. These individual lattices, they can actually oscillate as well. On top of that, there should also be a gapped Higgs mode, which in this case is an oscillation between the BEC background and the crystalline nature of the system. And you can, for this infinite system, in a fairly straightforward way, calculate the dispersion relation. For dipolar gases, there's this famous thing that it bends over at a finite momentum and has this minimum. This is the so-called roton minimum of the dispersion relation. And you will see what happens now as we approach the transition. This gets softer, and so this is actually what gives you the length scale of this crystal eventually. You already see there's kind of a periodicity emerging here, so we can actually restrict ourselves to the sort of first Bragg zone of this crystal, where we actually then find 3 modes right at the transition point. At this point, it's not clear which one is which, but if we move a little bit further, you see one of them actually moves up. That's the Higgs, and the other ones are the 2 Goldstone modes. So much for the simple case. In reality, everything happens in a trap, and there things get a little bit more messy, but you can still calculate all the excitations in the very same way using the so-called Bogoliubov-de Gennes equations. And so let me walk you through this picture here. This is now the tuning parameter, the S-wave scattering length of the contact interactions as we transition from BEC, which is on this side, to the supersolid, which is on that side. Now the thing in a trap is that the modes cannot really, the gap cannot really close anymore because the lowest energy excitation is always the dipole mode. So the easiest thing you can do is have the whole gas basically slosh back and forth in the trap. As you can see here, that's the lowest one. Then you have the quadrupole mode, the gas is breathing, and so on and so forth, many more modes. That's the usual BEC excitations. And they're sort of defined by the trap in this case. But then you see there's something interesting happening here. There's some mode that softens, and that's this roton mode that I was just showing you in the infinite system calculation. And actually, if you look close enough here, there's 2 kind of roton modes in this system, one symmetric and one anti-symmetric with respect to the trap center. And that's because a roton is really just a perturbative modulation on top of this BEC at this point. And so energetically it makes no difference whether it's shifted by half a wavelength, and then this gives you basically 2 degenerate modes here. And they're now interesting because they're defined by these dipolar interactions in the system. Good, then you see, okay, they split now right where we think the phase transition is happening at a finite gap. It's again because it's a finite system, so there's a gap remaining. But you basically get a Higgs mode, which stiffens right away, and you see in the animation really how this is an oscillation between the BEC and the crystal modes. It hybridizes here, so there's no symmetry protecting this in this system here. It just lives for this small range of interactions where there's simply no other mode. And then you get fairly complex oscillation patterns which have been observed in related experiments in Innsbruck and Pisa. What we are mostly interested in is this low energy Goldstone mode here, and I will come to this in a second. First of all, we can now take all of this together and really say something about supersolidity, because as we cross this transition, we can look at the in situ pictures and really see how the crystal emerges. Then we do these interference pictures, we see there's a region where this crystal is coherent. And now we can study this Goldstone mode, using a correlation analysis. We can't just look at this mode because it's so low energy that it takes forever to oscillate. But there's a statistical analysis that we can do, because what happens in this mode is actually an out-of-phase oscillation between the BEC and the crystal structure. That's a thing, again, related to the trap. So this involves very obvious Josephson dynamics, so a hallmark of a superfluid. And we can basically look at correlations between the displacement of the crystal and the height of these droplets. And I'm not going into details, but of course, this signals here that right where we have the coherence, also this mode emerges. So there's really these modes associated with the phase transition. We can also observe the Higgs mode. And basically this tells us it is really a superfluid state of matter also, and then the supersolid state of matter does exist in these droplet arrays. Good. Of course, once you observe this, you want to learn more about it, and one way forward for us was to actually look at fluctuations across the phase transition. Why fluctuations? That's of course not something entirely new, but it's something very nice because it's related to so many interesting things, like, for example, of course, the phase transition is inherently connected to this, but also correlations, the excitation spectrum, thermodynamics, and the dynamic response of the system. So there's a little bit for everyone. The way we can characterize fluctuations is using the structure factor. And what is the structure factor? It's just the Fourier transform of the density correlation function. It's historically quite interesting to use this because that is how people learned about superfluid helium in the first place, by doing neutron or X-ray scattering on helium. And it's, of course, something in our ultra-cold community that is very well known, where it's usually measured by Bragg spectroscopy. Now, if there are any experimentalists here that ever had to set up and tune an apparatus for Bragg spectroscopy, they will know this is not a lot of fun, which is why we took a different approach to this and measured the static structure factor, which is actually directly related to the in situ density fluctuations. So you take the in situ density fluctuations, turn it into the power spectrum, and that basically is the same as the static structure factor. Now, that's very nice because it gives us simultaneous access to all momenta. We don't have to tune any laser beams. And it's directly linked also to the excitation spectrum. So it's very nice for me now to illustrate what it really means. So here's again this excitation spectrum that I was showing you before. There's sort of already a roton minimum starting to emerge. And here's the corresponding structure factor. And now we will again approach the transition. You see there's this roton minimum emerging, and at the same time, there's a strong peak coming up in the structure factor at the same momentum. So as the roton softens, fluctuations and the structure factor get dramatically enhanced. So we can do this in an experiment now by taking hundreds of pictures across this transition. We calculate the mean image and then the fluctuations around the mean. So this is one set of fluctuations. Here's another one. And there's, again, like I said, hundreds more. And then we obtain the mean power spectrum by a Fourier transform. And that basically gives us the structure factor. So now we can look at the structure factor across the transition. And let me give you a reference length scale here, which is the spacing between these droplets that I was showing you before. And so you see, we start somewhere deep in the BEC. There's not so much going on. There's a little bit of roton population here already. But then as we approach the transition, there's a little shift of this roton peak that's actually in agreement with a variational approach. You don't have to do very fancy theory for this. Then the amplitude, as you can see, dramatically increases. And it actually sort of is the precursor for the transition already. It gets so high, we know already that temperature plays an important role here. The gap closes, and then thermal fluctuations basically populate the roton modes. Right at the transition point, actually, the roton momentum here matches the droplet spacing, and this is why I was showing you 1D pictures in the beginning. You can very nicely, adiabatically just ramp your scattering length, and you will end up in the ground state of the system. Everything fits, basically. And then you go on, and then at some point, things become more messy, and I will show you in a second that the splitting of this roton mode here is actually the emerging phonon modes of the crystal. Yeah, so for now, this is just experimental data, no analysis yet. Down here is a BEC, supersolid, and then the classical crystal. I should actually go back once. This has not been calculated before. This is incredibly hard actually to calculate. So if you want to do it, here's the data to compare to. Yeah? But we can learn more by doing a so-called principal component analysis. So that's a statistical analysis of these data sets to find the dominant fluctuation patterns. Yeah? And on the BEC side, it has been established that these patterns can directly be associated with the Bogoliubov of the Gen modes that I was showing you before. And so the dominant modes on this side should be these two rotons. You remember them, yeah, the symmetric and antisymmetric one. And indeed, these are the ones that we find in our analysis, and they're really enhanced in terms of population right at this transition point. We can actually also extract these patterns and compare them to Bogoliubov of the Gen theory. You see they look very nice. One is symmetric, one is symmetric, one is antisymmetric. And the fluctuations right at the transition point even get so strong that we can see a roton fluctuation pattern in single shots sometimes. Then we can look at the next strongest modes. We see more BEC phonons and the crystal phonons. Actually, if you Fourier transform the crystal phonons, you see this double peak structure. You can interpret this somehow like a reflection at the edge of this emerging Brillouin zone. And this gives us this extra structure in the structure factor. Yeah? And then the nice thing is, if you follow the weights of these modes now, you start on the BEC side, and then of course the BEC phonon is still dominant, but that decreases heavily as you go into the supersolid and crystal regime. At the same time, the crystal phonons increase in weight, and in the middle, in the supersolid regime, you actually have both, because it is a state of matter that has both properties of a BEC, and it has properties of a crystal. So the supersolid region really supports both, as you would expect. I'm going to be brief about 2 dimensions. You can basically do the same thing. Yeah? You remember this picture that I was showing in the beginning of a classical crystal. There's many more modes in this. There's even new ground states in 2D, where BEC is no longer this inverted parabola that you learn about in your lectures, but it becomes a blood cell-shaped entity. You can extract all these same structure factors as well. You see here excited blood cells. They only come as excited states because they live so close to the transition. You can actually extract from a radial analysis of the structure factor that there are actually 2 modes softening now in 2D. M equal to 2 and M equal to 3 roton. Yeah, the quantum number is sort of associated with the radial degree of freedom. And this also agrees here with calculations that we do again with Bogoliubov-de Gennes. And you see there's now sort of a mode competition between M equal to 2 and M equal to 3 rotons. One actually is a triangular lattice and one is a square lattice. And so it's actually very hard to get into a ground state here because this time it doesn't fit. What does this mean for a 2D supersolid? It means actually that you need to take many, many more atoms into account in your experiment. You need to cool many more atoms, and then actually M equals 3 becomes dominant. So if anyone is interested in the discussion about 2D supersolidity, please come and see me at the dinner table. But there's actually more than just droplet crystals. So I want to sort of conclude with some nice pictures here. These droplet crystals are one thing, but it turns out if you calculate the phase diagram in 2D, there's much more going on here. And so what you get are actually not these droplet supersolids, but for example, also honeycomb patterns like this one. And so what is going on here? It turns out for these dipolar droplets here, which contain, of course, hundreds of atoms, there is a maximum density that they can have because of energetic reasons. Yeah? And so at some point, as you increase the particle number in such a droplet, it becomes actually energetically favorable to flip the density and actually fill the holes between the droplets rather than the droplets themselves. And this is how you get such a honeycomb pattern. There's not such an intuitive argument for the other patterns that you get, this labyrinth here and these pumpkin or cogwheel patterns, but it's basically also just energy considerations that lead to this. Why is this interesting? Because actually the same kind of patterns, they emerge all over this, basically in all sciences, from these classical ferrofluids that I was showing in the beginning. If you search on YouTube, you will find very nice videos of this. But even in the animal kingdom here, in chemistry, in computer science, and of course also in physics, for example, in the strongly correlated Fermi matter of a neutron star. So that's very interesting, and here is now a system where you can really have tunability and everything to look for this. The problem is if you calculate the phase diagram, this is the region that we can currently explore in experiments. You see again, we need more particles, and there are new experiments under construction to actually reach these interesting states, not only in our group, but in several labs actually. But there's another way, and that actually brings me to the molecules that Immanuel was mentioning. We can also use larger dipoles, because the equations that govern this system, they have symmetries, where basically increasing the dipole is very, very similar to increasing the particle number. And so in the end, what it gives you is a lower saturation density. Yeah? So these states here should actually move to lower particle numbers. And that's exactly what happens as you increase the dipole. They move to more realistic particle numbers here. But then again, so the magnetic moment is already maxed out, corresponding to this number here in dysprosium. And so the only way to actually get there would be electrically dipolar molecules. which, as you may know, are hard to cool. We heard about it earlier today already. And so there are no molecular BECs yet, but of course, many labs are trying now, and we're trying as well. And we're using very similar techniques to the ones that Dave has been discussing earlier today. And so we're basically running 2 experiments now, cooling barium monofluoride and calcium monofluoride by direct laser cooling. Barium monofluoride is actually a very hard molecule to cool because it's very heavy, but this makes it very interesting for these kind of precision measurements that you heard about earlier today, whereas calcium monofluoride is sort of starting to be established as the new rubidium of molecules. A little bit easier to cool, hopefully, and so we're working in this direction. What all these molecules have in common is their humongously large dipole moment compared to dysprosium, and of course, tunability of this dipole or of the dipolar interactions. So if cooling turns out to be feasible, there's of course another elephant in the room here, which is collisional stability, but it was recently shown by microwave dressing we can address this and make these molecular gases stable, with important contributions here also from MCQST in Emmanuel's group. Our little contribution to this was recent work where we actually realized that in these tuned interaction potentials that you get when you microwave dress these molecules, there are also scattering resonances, and so this should really give you the independent tunability of dipolar interactions and contact interactions exactly as you would need to explore these phase diagrams that I was showing you before. So with this, there are many exciting experiments ahead. I will actually skip on this. I just want to mention one thing. Last thing that we realized when looking at this was that actually there's this vacancy-induced supersolids that were there from the beginning. And now we've realized these droplet supersolids. And it turns out if you make the dipoles of the molecules really large, they can actually interpolate between these 2 limits. So sort of molecules should really help us to find a universal picture of this supersolidity here. With this, I have the conclusions here. I'm looking at Emmanuel, who's getting a little bit nervous. I actually want to skip my conclusions and show you 2 more slides of something completely different, because this is actually all quantum science so far, and this conference is about quantum technology as well. So, if you want to read about it, there's also a Physics Today article that I wrote recently. So the problem with these experiments is obviously they're very, very complicated. You need a lot of lasers, a lot of stuff. It's complex, it's fragile, it costs a lot, and you need a lot of experts to actually run this. And so what we thought is whether we can build something more compact, something that can eventually fit into a shoebox. And our approach to this is actually 3D printing. So this is a normal optical fiber that you use in your experiments. And we 3D printed a lens on top of this. And this can realize an optical tweezer. So very, very compact. The technique is 2-photon polymerization. You can basically create almost arbitrary shapes. This is a total internal reflection lens. You can build spheres. You can even put this onto a multimode fiber or multi-core fibers and create atomic arrays. It's plastic, so you would normally not put it into your vacuum chamber, but it turns out it actually works surprisingly well. There's no issues with this, and we can even trap atoms close to it already. We can move the whole thing around. It's robust. It can sustain all the alkali pressures in the vacuum chamber, so it's all very nice. And so hopefully, as a next step, we can realize trapping and detection of single atoms in such a microscopic package. And with this, I'm now really at the end, and I thank you for your attention.
Yeah, thanks a lot, Tim, for this very nice talk at the end of the day before the poster session and lunch before. Are there questions, comments? Yes, Robin, do you want to? I pass on to you.
Yeah, thank you for the very interesting talk. I was wondering if you can say something about the lifetime of the supersolid phase, like how quickly do neighboring droplets decohere, and what's the main source of decoherence here?
So the main problem in these experiments is basically that in dysprosium, I mean, I was brushing over this. I said, okay, you can just tune the contact interactions as you can for all other atomic gases. The problem is that it's a very complex scattering process in dysprosium, and there's hundreds and hundreds of Feshbach resonances, and depending on whether you pick the right one or a bad one, your lifetime can be anything between say 30 milliseconds and 200, 300 milliseconds. So if you pick the right one, there's no issues. But it's all limited basically by the high density in these droplets by free body losses. And that's actually also an argument for molecules, because it turns out all this shielding should also shield against free body losses. So molecules should really be the superior system to study this if you are interested in even longer term dynamics.
Hello, this is a very nice presentation, and I have a question on the 3D printed tweezer array. I just wondering how is the scalability of this printed tweezer array, and can you trap a lot of atoms to do the many-body physics with such a technique?
Yeah, so in this case, I mean, this was really just our little proof of principle experiment that we can stick this into vacuum. These traps, they were designed to really be tight enough to really trap only a single atom. But in principle, yeah, I mean, anything can be printed. So these techniques, actually, we did not invent them. Really, I should not take credit for this. This is very popular now in the optics community. They are printing endoscopes or something like this that you can put on a fiber and use on patients, or in biology for tweezers, this has been used. And so if you want to make an array, you would have to put it on a multi-core fiber. Of course, there's a lot of discussions whether you can have, for example, Rydberg atoms close to such a fiber, but you can put coatings on this as well. And so we're just exploring this at the moment. So, but it's a lot of people are doing this as well, also for ion traps, for example. Ion traps are 3D printed in this way now as well.
Very good. Are there more questions? Yes, and let's take. Wait, let's give this one here. Two more. Yep.
Thank you. I have one question. Did you determine the critical exponents for this superfluid, supersolid transition?
Yeah. So I was brushing over my important questions to answer next part. The nature of the phase transition is really very much uncertain here, because it's such a small system. So it's basically all dominated by finite size effects. And so to really study things like critical exponents, for example, you really want to make larger systems. Otherwise, there's no real thing, like no real way of answering these questions. There's certainly no jump here in the superfluid fraction. It's sort of a continuous decay, but it's all very complicated to measure, and so larger systems is really the way to go.
One more question in this direction. What about the temperature in the system? So this BEC that you start with, can I think about it as a pure BEC where I can really ignore temperature, or aren't these processes like heating the system that I also have to worry about a normal component in the material which might give me additional modes and make everything even more complicated?
Yeah, so in these experiments that I was showing you, you can consider the BEC as zero temperature, basically. What you can, of course, do is basically set all your parameters such that you end up in a supersolid and then evaporatively cool. And then obviously temperature has something to do with this, and there's some interesting studies, for example, by Francesca's group in Innsbruck, looking at what comes first. Is it first going to form a BEC and then this crystal emerges? But that is all still ongoing work also. It's very hard on the theory side actually to describe this. So there's no real proper finite temperature theory for all of this yet. And temperature certainly is going to play a role, even on the very basic level of, for example, renormalizing the interactions here. So this simple Born approximation picture with just contact interactions and dipolar interactions at finite temperature, that even that may not necessarily be true. So it's a very complex thing. Yeah.
Thanks.